All right, we're gonna walk through the biochemical map, a basic overview so you can see everything. So looking at the breakdown of carbs, fats, and proteins. So we'll start with the carbohydrates. The big focus here obviously is glucose. We'll discuss a couple other sugar molecules, the galactose as well as fructose. But the main thing in all of these pathways is glucose. So you can either take glucose over to glycogen or glycogen back to glucose. You can take glucose through glycolysis to pyruvate, or you can go back the other way and turn the pyruvate into the glucose through gluconeogenesis. So we're going to go through these individually real quick. So on the glycogenolysis and glycogenesis, it's all on this part right here. So basically, if we start with glucose and we want to turn that into storage, so say you just ate a big meal, you get an insulin release, you don't need to use all of that right away or need any extra energy, so you want to store it. So you can go right up through this way and turn it into glycogen. And then say the opposite is true. Now we need to have a little more energy, and we've got some things over here that stimulate that release. We're going to take glycogen down this way into glucose the other way. So that's the glycogenesis and glycogenolysis. So then the big thing with the glucose metabolism is the glycolysis pathway. And this is this huge pathway here. And basically the point of this, we're wanting to get to this endpoint of pyruvate down here. So you're starting at glucose. Important things I want to point out here. First, you're getting a net of 2 ATP, okay? You'll see up at the top, you're losing 2 ATPs, and then as you go down here, you're gaining 2 ATPs. But this part right here, the DAP will go over, and you'll go through that again, so you actually get 4 ATPs. So you're getting a net total of 2 ATPs from this process. And the other thing I want to point out with the glycolysis is there's 3 irreversible steps. They're in red. So here, here, and here, okay? And the rate limiting step up here is the phosphofructokinase enzyme there, okay? Another thing to note is fructose or other sugar. So again, they're the main, the glucose, fructose, and galactose. The fructose comes into the pathway here. This glyceraldehyde, it can go to fructose 1P, and then the glyceraldehyde, which can actually go all the way back over to this glyceraldehyde 3P here. But this is where fructose comes in. We talked about in lectures that this was kind of like the back door because it doesn't have to go through this rate limiting step here, okay? And then again, this pyruvate, you're going to go from here and take that into acetyl-CoA and then into the Krebs cycle. But before we get into that, I want to talk about the reverse, which is actually gluconeogenesis. So when you want to go backwards in this pathway, you want to take the pyruvate up to the glucose again. There's these 3 irreversible steps. They're the one directional arrows there, so it's only going one way. So you have to have roundabouts on gluconeogenesis to get back to glucose. The first one is this malate shuttle here, so we can't go from pyruvate back up to the PEP here, so we're going to go into the mitochondria. And as a side note, everything in yellow, like this yellow or this yellow, is in the cytoplasm. Everything in the red is the mitochondria. So we're taking this pyruvate here from the cytoplasm into the mitochondria. We can't get back out going this way, so we go around this malate shuttle, and then we can bypass that irreversible step. Now on gluconeogenesis, there's 2 other irreversible steps. Remember we talked about them right here and right here. So what I'm going to do is I'm going to move this over to just kind of show you on this. So instead of going from this fructose 1,6 bisphosphonate up here, we're going to use a different enzyme, the fructose 1,6 bisphosphonate, to get past that step, okay? And then we can still use the isomerase. That goes either direction, so we're over here. But here is a one-directional. We can't go from glucose to glucose 6-phosphate. We can't take it back. So we're using this new enzyme here, the glucose 6-phosphatase. So that is the gluconeogenesis, is finding a way around those 3 irreversible steps. Okay, so we talked about fructose and we talked about glucose. Where does galactose, the other big sugar, come in? So you get your galactose from your lactose, so that breaks down into glucose and galactose. So galactose can be broken down into this process here, and then it can go straight into glycolysis, again at this glucose 6P part right here. Or, you know, you can start at the beginning as glucose there, but that's how the galactose actually breaks down. If it gets too much and you can't, if you're overwhelmed with the galactose, it can go into the lens and cause cataracts and other issues. So that shows that. Also, just as one last point with the glucose metabolism, there are other things besides glucose that can be utilized to enter into the pyruvate and eventually the Krebs cycle. So this is just a little map showing that 3 main things here: glycerol, lactate, and amino acids can all be used to make the pyruvate that goes into the Krebs cycle through these interactions. So this is the fructose 6P and the glucose 6P from up here in the glycolysis cycle. But basically, when you don't have oxygen, I didn't say this earlier, but in the electron transport chain, the oxidative phosphorylation, you need oxygen. When you don't have oxygen, the pyruvate can't go forward, it's going into lactate. Now this can be changed the other way, but when your muscles get that lactate buildup because you've used all the oxygen in the muscles there, that's that lactate buildup, okay? But you can change that and change the lactate back into pyruvate. Glycerol, again, can go into this process, and it comes in at this DHAP. We talked about that with the triglycerides, okay, and the fat synthesis there. That's how that all fits in, okay? And then finally, these various amino acids and their carbon skeletons can all go into these things. And this is our malate shuttle we were talking about earlier, and they can all be broken down and used in these various things to make the pyruvate, the oxalacetate, malate, all of these things. So those are some other non-glucose things we can use when we're trying to synthesize these things. Okay, so now we've got down to pyruvate. We're going to take this pyruvate into the mitochondria again. Now this step, the pyruvate dehydrogenase with a couple other enzymes here, it's a complex because you've got a couple others, we're going to make acetyl-CoA. You notice there's all kinds of B vitamins in here that are needed to do this. The acetyl-CoA then is what's going into our Krebs cycle. So this Krebs cycle is really the money shot because it combines a lot of these, okay? The Krebs cycle, the whole point is to produce these electron complexes that we can send into oxidative phosphorylation, okay? So we're going around this, and there is a lot of coming together from the amino acid site, even the fat sites, to make all this happen. This is why it's kind of in the middle here. It's kind of the common ground, lots of things. We got a rate limiting step here, the alpha ketoglutarate dehydrogenase complex. We'll talk about in a minute when you get some of the protein breakdowns, a lot of them come into the cycle too. Their carbon backbones are used to make a lot of these, and I've got a picture of that here. We'll talk about that a little bit more. But when you go through this, all of this goes around. It can go either way except 2 steps. The 2 rate limiting steps, again, this alpha ketoglutarate dehydrogenase as well as the citrate synthase are the 2 rate limiting. Those are the only unidirectional arrows in this. Everything else can go back and forth, okay? But once we've gone through this, we get our electrons, our NADH and our FADH, and they're coming over here, okay? This is in the inner mitochondrial membrane, and there's 4 complexes to the electron transport chain. Notice here you got iron and copper that are needed in complex 3 and 4. But basically, these electrons are going from the NADHs and FADHs in complex 1 and 2 to CoQ10. And then you've got these cytochrome coupled with iron in complex 3 that these electrons are passed to. And then after all of that, they go into the oxidative phosphorylation where you have all these electrons culminating. You've got a gradient here that pushes all these hydrogens we had coming out as we did these complexes are now accumulated, and when they go down the gradient, they produce the ATP. And then the ATP can go out and live its best life in all of the places it's needed for energy, and another ADP molecule comes in here and is converted to ATP again. So that's the whole thing, the whole point of all of this is to get stuff to go to the TCA cycle, to make these electrons to go through here so that we can have ATP, which is our energy, which is the important part, another like version of how that goes here. But that is really the important part. I also want to point out, anytime you're seeing these NADHs and FADHs, you need your B3 and your B2 there, okay? So I kind of wrote that in for this one, but anytime you see that anywhere throughout the NADHs and the FADHs, you need your B3 and your B2. And I put that in a key over here as well, telling you about the colors again, and then any of these NADHs or their derivatives are the B3, FADHs are the B2. Anytime you see PLP, that's got B6 with it. It's just a form of the B6. And then anytime you see TDP or TPP, it's got thiamine. And coenzyme A also is B5, okay? And the transketolase is thiamine. So anytime you see that those contain those cofactors there. Okay, a couple last points on the glucose cycles is, one, over here at this DHAP step, you can actually go down here and get like the glycerol and the triglyceride synthesis out of this part of the pathway, and they can also go into this and then enter into glycolysis or gluconeogenesis. So that's one way that like the fats can tie into the carbohydrates. So there's plenty of these, but I just want to point that out. And then also what we didn't discuss was the pentose phosphate pathway or the hexomonophosphate shunt. So this step right here of glucose 6-phosphate, you can actually go into the pentose phosphate right here, and you get a rate limiting step right here with this glucose 6-phosphate dehydrogenase. And this uses a breakdown. It breaks down into these 5 carbon monosaccharides, which is the pentoses. That's where you get this pentose phosphate. And it also can produce this the nucleotides at the end of that. So that's another option that can either be going through the rest of glycolysis there, or it can go into this pentose phosphate to make those nucleotides and those 5 carbon monosaccharides. And I've got another thing here that just kind of shows that relationship here. You're looking glucose 6-phosphate, and here you go. You're going into the pentose phosphate pathway, or you can go on down and do pyruvate and the Krebs cycle like we just talked about. So that's another option there. So now let's talk a little bit about proteins. So proteins here, we have got these reactions. So basically with amino acids, we're breaking them down into ammonia, which gets excreted through the urea cycle, and we'll talk about that in a minute. And we have carbon skeletons that also get formed. And these are through these reactions that we call transaminase of amino acids. So here's an example. Common enzymes used are the ALT and AST, found in the liver, AST also in the heart. But basically, this helps kind of transform these amino acids into different amino acids and these alpha keto acids, or these carbon skeletons. And we can use this process to get those non-essential amino acids or change those non-essential amino acids into the essential ones that our body doesn't make. So we can use these transaminase reactions to do that. And we'll talk about the fate of those carbon skeletons that we get and how those are all utilized in a second here. But as far as these go, most amino acids do undergo the transaminations. One of the couple that doesn't is this threonine. So the other reactions that you can get is deamination. And what that means is you're simply taking off the ammonium right here. You can see that. So you end up with this alpha ketobutyrate skeleton here plus an ammonium. So you're not doing like with the transaminations, you're switching from one to another. And this one, you're just simply taking off the ammonium. That's the deamination reaction. So I showed you a couple of those with the glutamate. Here you go, and you get the alpha ketoglutarate out of that. That's used in a lot of different reactions. But basically, you're just taking that off with the ammonium, okay? So once these amino acids have undergone these transformations, this is the deamination. You can also have the amination where you add on an ammonium, so that also happens too, just to let you know. We didn't have to do it for the map, but that can also occur too. So once you get these ammonium atoms, then you have to get rid of this. You have to get rid of it because you don't want it to accumulate and cause all kinds of issues. So that's where the urea cycle comes into play, okay? So starting in the mitochondria, you're working your way out here, and then you go into the cytoplasm. So any of these tan ones you see can be in both the mitochondria and cytoplasm happening. So this part's in the mitochondria, this part's in the cytoplasm. So rate limiting step here is this arginosexate synthetase, and basically you're going around to here, and then the urea is going to the kidney and is excreted through the kidneys. So that's the whole point of this. Now the urea cycle and the tricyclic acid cycle are related to one another. And again, here's some overlap between these cycles. So as you can see, the oxaloacetate in the tricyclic acid cycle can go to aspartate, and then that can go on into the urea cycle. And there's several other reactions. Here's a transamination reaction happening that produces pyruvate that can also be used for that. So you can see these overlaps happening, and this is kind of a visual demonstration of how those overlaps between the urea and the tricyclic acid cycle interact. All right, so we said we're getting rid of the ammonia here, but we have these carbon skeletons. So what becomes of those? The carbon skeletons or the alpha keto acids can go into so many things. They can be used over in fats when we talk about ketone production. They can go into the glucose cycles and be used there. They can be used for cholesterol and fatty acids. There's a lot of things that can overlap that these alpha keto acids or these carbon backbones are used for. So just one demonstration here is with the tricyclic acid cycle. Again, you can see like all of these amino acids and then their carbon skeletons can be used to make these different pieces that we use in that urea, or I'm sorry, in the Krebs cycle here. So that just kind of shows you one little piece of how all these amino acids, like look how many of them can go their skeleton there to the alpha ketoglutarate to be used. So that just gives you one thing, but those skeletons are used for all of these processes and breakdowns, and they're happening all over the place. So just to note that. Okay, and finally we got fats. So basically these triacylglycerols, they are in the adipose tissue. And when we need energy, such as we're fasting or maybe we're eating low calorie or exercising, whatever, they get released. And there's basically three main enzymes here, okay? And through hydrolysis, these three enzymes help release these from the adipose tissue, all right? And once these are released, again, we talked about how we can use this in the glycolysis pathway, or we can turn these through the beta oxidation and go into the tricyclic acid cycle, which we're going to show you here. So once we've released these and we've done the hydrolysis step with these three main lipases there, the first activation step is taking the fatty acid and we activate it by adding on an acetyl-CoA to it, okay? and that is then acetyl coenzyme A, and it can then travel from here. We take these fatty acetyl coenzyme A and we use the carnitine shuttles. Now, the short and medium chain ones don't have to do this. They can go right on through, but if it's a longer chain, they have to use this carnitine shuttle because we can't take this directly into the mitochondria. So we change it. We take the acetyl-CoA off, put carnitine on it, and then it goes through, and then we replace it and we reuse that carnitine. So it's a shuttle to get it into the mitochondria. From there, we undergo beta oxidation, which is this. So there's 4 main steps. You get oxidation that produces FADH, hydration, which gives H2O onto it, and then we get the second oxidation that produces the NADH, and then we get a cleavage step to get the acetyl coenzyme A. And then look what we got here, the fatty acyl coenzyme A and the acetyl coenzyme A. Now we can go to our favorite place, the Krebs cycle. Okay, so that's how this, here we go, acetyl coenzyme A. Now, say we don't have even chain, because this beta oxidation, this 4 steps is a repeated thing. So every time you're getting these 2 acetyl coenzyme A, these carbons, 2 carbons off of it each time. So if it's, 16 long, you have to go through this process 7 times, okay? It's repeated steps. Say it's odd, it's an odd chain, okay? Well, then you're left with this 3 chain carbon right here. So with this, you can break it down into another step here, and the succinyl coenzyme A can go over from here into the citric acid cycle, okay? So that is right there, succinyl coenzyme A. So if you have an odd chain fatty acid, when you're breaking it down with beta oxidation, you do 1 further step here to get that into the Krebs cycle. Now also, I've got a little thing here that shows you where all these acetyl coenzyme A's can go. And, we talked about with the Krebs cycle. But you can also, again, do the cholesterol fatty acid thing where we can go back up, and we'll talk about that in a minute. But also another big one is ketogenesis. So again, think about your fasting states. Think about, if you're eating a really low carb diet, okay, and you need these, then you can go into this ketogenesis. And this is this process where you get into the beta hydroxybutyrate and acetone, and those are your ketones. Okay, so the acetyl-CoAs that you get from the beta oxidation can go into this process as well. All right, so say we don't need any more energy, okay? The beta oxidation, we're breaking these things down to go through Krebs to get more energy, okay? Say we're backed up, and you can see that when your citric acid, your isocitrate, they get more in there and it's backed up a little bit because we don't need any more energy right now, okay? So we can actually go backwards and do some fatty acid synthase, okay? So what happens is we've got the acetyl-CoA, and we're going to go make some fatty acids now. So again, we can't just go right out into the cytoplasm from here, so we need another shuttle. That's where our citrate shuttle comes in. So our acetyl-CoA comes in here, and we use the citrate shuttle to get it across into the cytosol. From there, just like with beta oxidation, we had this activation step where we added on this acetyl-CoA synthase, or we use that enzyme to add on. We have an activation step for this one, and that's the formation of malonyl-coenzyme A from the acetyl-CoA and CO2. That is our activation step to make these fatty acids, okay? And finally, then we go into this complicated process, just like we broke down beta oxidation, 2 carbons at a time. This time we're adding it on through this complex set of reaction that repeats over and over again until we build up a fatty acid chain. So it's kind of the opposite of the beta oxidation. You're going backwards. Both of them require, like the carnitine to carry over on the beta oxidation. This is the citrate shuttle for the fatty acid synthase. And then this long process of adding on the 2 carbons again to go back to our fatty acids for storage when we're in a high energy state. So that is my basic overview of the biochemical map.